Good afternoon, everyone. Welcome to session 2 of day 8 GATE 2021 online training program. I would like to introduce today's speaker, Dr. Umesha P K, to everyone. Dr. Umesha P K is currently working as a professor in the Department of Civil Engineering in BBC, Mysore. He has completed BE degree in civil engineering from the University of Mysore in 1980, securing second rank. Master's degree in structural engineering from Indian Institute of Technology, Madras in 1982, and PhD degree in 2002 from University of Mysore. Sir has worked as project associate in IITM for ISI project on typification of industrial structures during 1982 to 84. Later, he joined Structural Engineering Research Center, Madras, as scientist during 1984 in computer-aided analysis and design in computational mechanics. He served as head of tower testing research station of CSIR-SCRC Chennai. He is actively involved in research and consultancy for more than 3 decades. He has handled more than 10 crore consultancy projects for government and private companies, both national and international. So with this brief introduction, I would like to welcome Dr. Umesha P K to the session. Over to you, sir.
Thank you, Professor Madhushri. So now I would like to present on solid mechanics. Okay, solid mechanics, we have the syllabus, bending moment and shear force in statically determined beams, simple stress strain and their relations, simple bending theory, flexure and shear stresses, shear center, uniform torsion, transformation of stress, buckling of columns, combined and direct bending stresses. So firstly, I would like to tell what are the determined beams and indeterminate beams. So simply supported beam, overhanging beam, cantilever beam are the determined beams. Indeterminate beams are fixed beams, continuous beams, propped cantilevers. Moment, it is the product of force and perpendicular distance between the line of action of force and the point about which the moment is required to calculate. For example, if you have a beam, then you apply the force. So this is the distance we have here from the fixed end. So this is the distance you are measuring from here. That perpendicular distance between the action of force and the point about which the moment is required to calculate. Bending moment, the moment which causes the bending effect on the beam is called bending moment. It is generally denoted by M or Bm. So I would like to tell what are the sign conventions. So bending moment is considered sagging bending moment if it tends to bend the beam to a curvature having convexity at the bottom as shown in the figure given below. Sagging bending moment is considered as positive bending moment. So you can see here, so it will be having the sagging, that convexity at the bottom. So it is called as the positive bending moment. And the negative bending moment, if you see, similarly the bending moment is considered as a hogging bending moment if it tends to bend the beam to a curvature having convexity at the top as shown in the figure given below. Hogging moment is considered as negative bending moment. See, this is the, if you say this is a bending moment, it's acting in a reverse direction, it will be convexity will be upwards. So it is hogging bending moment is negative, sagging moment is a positive. Then convention for the shear force. So if you take a section, left side it is acting upward and right side it's acting downward, it is considered as the positive shear force. And similarly, if the section in along the section, if the shear force acting left side of that one it is downward and right side of that one is upward, it's called negative shear force. Then if you see what is the bending moment diagram and shear force diagram. Bending shear force diagram. The diagram shows the variation of shear force along the length of the beam is called shear force diagram. Bending moment diagram. The diagram which shows the variation of bending moment along the length of the beam is called bending moment diagram. So I would like to take, also you tell me, let us know what is the point of contact flexure or inflection point. So point of contact flexure is the bending moment diagram in the bending moment diagram where the bending moment changes its sign from positive to negative or vice versa. It's called point of contact flexure. It's also called inflection point. At the point inflection of point contact flexure or the bending moment is zero. So I would like to tell what is the relation between the load, shear force, bending moment. So if you take an arbitrary beam, simply supported beam having a arbitrary load, as shown here, is a general type of loading. So here let us consider is the differential element of length, dx at the section between the section xx and x1 as shown here. So this is a simply supported beam. Here it's called a hinged support. It is a roller support. We'll be having the arbitrary loading, that is a W kilonewton per meter. So we'll be considering as a differential element. It is for a length of dx. So here you take a length of ds here. So if you take a free body diagram of that element, then it is called, so we'll be having the loads acting left side as well as right side. So left side, if you see here, the shear force V is acting here and moment is acting here. And the right side will be having the V plus dV is a incremental shear force, V plus dV, and incremental moment M plus dm at the section x1. And also it will be having the load W at kilonewton per meter. It is having for the length dx. So if you consider taking the moment at O, then what are the moment acting here at O? So moment M is acting, it is taking anti-clockwise, it is negative direction. Then M plus M, it is also acting anti-clockwise. So it is acting about the section, it is acting in the other direction. So it is M plus dm minus V into dx, that the distance V into dx is equal to minus, and also have the load W into dx. It is a total load acting over a length of dx at a distance dx by 2 at the middle of the section, that is dx by 2. So this is the moment if you are taking at the point O, then what you will have, neglecting the small quantity of higher order. For example, dx into dx is itself is a small quantity. If you take a square, it will become still less. So we'll be neglecting that one, and you will be having, if you neglect that one, V into dx is equal to dm. So it will be cancelled here, m minus m plus m, and here it will be having a dm only will be having this it will be cancelling this one this. So we'll be having V into dx is equal to dm. So finally we'll be having V is equal to dm by dx. That is the differential of a moment divided by differential of with respect to dx. So this is the relation between the shear force and bending moment. So if you differentiate moment with respect to x, you will get the shear force. Similarly, if you take the same section, so free body diagram will be having, and if you take the considering the equilibrium of sigma Fy is equal to 0, that means you will be taking all the vertical loads acting in the element will be considering as the 0. So that's what you will take the forces acting upward and downward. So V is acting downward minus V plus dV is equal to acting upward. So V plus dV, and V in W into dx. That is a force acting due to the load for the portion dx, that is minus dx, W into dx. So if you do that one, dV is equal to W into dx. We'll be getting the value like this. So W is equal to dV by dx. So hence, derivation of shear force with respect to x will get the force on the member. That is a different UDL, we got it. So this is the relation between the intensity of load and the shear force. So variation of shear force and bending moment, if you see for various standard loads are shown in the following table. See here, what happened, these are different types of load will be there, and shear force or bending moment will be there. So point between the loads or no load region. So shear force diagram will be the horizontal line. So that means point between the loads or no load region will be having the horizontal load. If it is the load is a uniformly distributed load, it is an inclined load. If it is uniformly varying load, it is a 2-degree curve. It's a parabola. So this is the shear force it will be having like this. What happened? The bending moment, if you have a horizontal line, it will be inclined line in the bending moment. And the inclined line, it will be 2-degree curve, that is a parabola. And if you have a parabola in the shear force diagram, we'll be having the cubic curve in the bending moment diagram. So this is the thing what you have to remember, variation of shear force and bending moment along the for different standard loads. So let us have a example. So I'm just taking a shear force and bending moment diagram for a simply supported beam subjected to point loads as shown in the figure. So this is the figure. It will be simply supported beam. So it will be having the hinged support and roller support. It will be having constant load of 5 Newton, 10 Newton, 8 Newton at C, D, E at the different distances as shown in the figure. So this is the thing. First, what you have to do, we have to calculate the reactions. How to calculate the reaction? So RA, this is a reaction at A is equal to RA, reaction at P is equal to RB. So what you have to do, solution using the condition sigma MA is equal to 0. So that means you're taking the moment at A. That is sigma MA is equal to all the clockwise moment is considered as a positive and anti-clockwise moment considered as a negative. So taking the moment at A, so RB into full distance, 2 plus 2 plus 3 plus 1, 8 meter, RB into 8. So that is acting anti-clockwise direction is the negative. Then 8 into 7 meter. So 3 plus 4, 7 meter. And 10 into 4 is also, it's all are acting in the clockwise direction. And 5 into 2 is equal to 0. From this one, you can calculate RP is equal to 13.25 Newton. So that means you are considering the moment at A, taking all the clockwise moment are positive, anti-clockwise are negative, and equated to 0, we'll be getting the reaction RP. Then we have to calculate RA by considering sigma Fy is equal to 0. That is the condition. So these are the basic conditions. Sigma MA is equal to 0, sigma Fy is equal to 0, and also if we have a horizontal force, that also sigma Fx is equal to 0 will be there. So RA plus, that is reaction RP 13.25 is equal to all the applied forces 5, 10, 8. So you will be getting the reaction RA is equal to 9.75 Newton. Okay, then you calculate the reactions RA and RP. Once if you know the reactions, then you have to go shear force calculations. How to do the calculations shear force? So you have to consider different sections. For example, in the beam I marked here 0, 0, 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, etc. So shear force at the section 1, 1 is denoted as V11. At the section V2 is denoted as V22, and so on. So if you want to calculate the shear force, see if you section, it will be there here. Left side of that one there is no force. So that is V00 is equal to 0 force. So that's why. So at the left side of the point O, that is a A, it will be 0. That is called as section 0 is equal to V01. Then we shear force at 1, 1. At the point just besides section point A, that is section 1, 1. So we will be having only the reaction, that is 9.75 Newton. So the shear force will be, it will be acting upward. So if you know the, consider our sign convention acting upward from the section, it will be positive. Then you consider at 2, 2. See, from point to section 1, 1 to section 2, 2, there is no force acting. So it is a, so that's a force, the shear force will be same as 1, 1. So shear force V22 is equal to 9.75. So then let us come to 0.33. So 0.33, we have the forces, reaction we have here, and applied load pi ton we have here. So reaction will be acting upward, that is a positive, that is 9.75, and V, it's acting downward. It is from the section it is acting downward is negative. So we will be getting 4.75. So shear force at VV at 33 will be V33 is equal to 4.75. So if you come to section 4.4, what happened? There is no force between 3.3 and 4.4. Hence, you will be getting the same shear force 4.75. Then coming to at section 5.5, that is 4.75, and up to whatever we have left side of 4.4, that is 4.75 will be there, and you will be having the applied force, that is 10 ton. So you will be getting minus 5.25. So similarly, we can calculate for other points, that is at 6.6. So you'll be having the same force as V55, that is minus 2.5, 5.25 is the Newton. And section at 7.7, 5.25 minus 8 ton, that is the minus 13.25. Then at 8, it will be also same. Then at the section 9.9, minus 13.25 plus that is reaction at RB 13.25. So this is the shear forces we have marked here at section 11, 2, 2, 3, 3, all the sections you got it, and we need to plot that one. So how to plot that one? Let us see that. And we have the reactions RA, RB, and RA is equal to 9.75. It will be going upward. Then it will be constant for 9.75. Then you have to come down by 5 Newton. So it will become 4.75. So constant from C to D, that is a 4.75 will be there. Then it will be coming down for a 10 ton, that is 5.25. Then 5.25 will be constant, and again coming down as 8 ton. So 13.25 will be there. So if you see the forces in the previous section, what are the calculated shear forces? So we have plotted here. This is the values of shear force diagram. So shear force diagram. So from the baseline, whatever it will be having, it will be positive, and down will be the negative. Then let us see how to calculate the bending moment. So this is the beam loading diagram. So reactions we have, reaction RA, RB, that is RA is equal to 9.75, RB is equal to 13.25. So all the loading acting on the beam you have. So first you have to calculate bending moment at A, denoted as MA, bending moment at B, denoted as MB, and so on, that is MC, MD, ME, etc. So MA, so it is simply supported. Since it is simply supported, the moment will be 0, and also at the hinged point, moment will be 0. So at the point A and B, the moments will be 0. So then let us calculate the moment at C. So moment at C, what are the forces acting at the left side of C? So we have the reaction at a distance 2 meter, that is 9.75 into 2. So since it is try to bend in upward, that is sagging moment, so that will be positive 19.5 Newton meter will be there. Then let us see the moment at D. So at the moment, either you can take the left side forces or right side forces. So MD is equal to, I'm taking the left side forces, that is 9.75 into 4 meter, the distance, perpendicular distance, that is 2 plus 2, 4 meter. And for the force, minus 5 into 2. So 9.75 into 4 minus 5 into 2 is equal to 29 Newton meter. So MD is equal to 29 Newton meter. Similarly, calculate the moment at E. So moment at E, so force, that reaction 9.75 into the distance from here to here, 7 meter. And for the 5 ton, the distance 5 into 5. So the 2 plus 3 is equal to 5 meter. And the distance for 10 ton force is equal to 10 into 3 is equal to, that is 3 meter will be there. So you'll be getting 13.25 at E. So you can take either right side, that 13.25 into 3. You will get same moment. So you see that one, MB is equal to, if you take all the forces from the left side, 9.75 into 8 minus 5 into 6 minus the 10 into 4 minus 8 into 1. So we will get 0. So that means you should get the force at B, the moment at B, you should get 0. That means you will be getting the chucking. So MB is equal to 0 since it is a roller support, simply supported support. So, okay. So hope you know all the how to calculate the bending moment if you have a simply supported determinant structure. Now let us draw the bending moment diagram. So you from the point, so you'll be having the points 19.5, then you will be having 29 here Newton meter, and you have the 13.25. So this is from the baseline, it is above that one. So it is called all the sagging moment, all are sagging moment, since the support will be simply supported, here roller supported. So it will try to bend in the bottom direction, that convexity at the bottom. So moment will be sagging moment, hence it is a positive moment. So this is a simply supported beam having the concentrated load. And let us take the bending moment of a cantilever subjected to load as shown here. So here we have the UDL and inclined load. So at a 30 degree at a 0.7 meter at a height here at a distance 0.5 meter, and the horizontal, this is the fixed end, this is fully cantilever, it is a free end. So A, B, it's a free end will be there. So let us see how to calculate the reactions. First of all, you have to calculate the reaction. So how before that one, so we have to inclined force, you have to resolve. How to resolve this one? This will be 30 degree. So horizontal force will be 40 into cos 30. That is horizontal force will be there. That is 34.64. Then vertical component of inclined force will be 40 into sine 30. That is 20 kilonewton acting vertically downward. So at a distance 0.5 here, and this will be at a distance 0.7 meter. So this is the thing. First, you have to resolve that one, because we know sigma fx is equal to 0, sigma fy is equal to 0, and sigma m is equal to 0. All these four different conditions, that is the three conditions you have to apply, equilibrium conditions. So now let us see how to calculate the reaction. Now whatever the horizontal force is there at a distance 0.7 meter in the previous one, so that can be transferred to the beam. So that is 34.64. So it will be transferring as a horizontal force at the point here, and a moment will be, that is 34.64 into 0.7. So that is what you are seeing here. So you will be calculating you will be transferring the force, horizontal force at this point, and a moment. And whatever vertical force will be there, that will be acting directly at that point. Okay. So this is the load you transferred. So now you are seeing it will be having the UDL, horizontal force, vertical force, and a couple. So all the things will be there. Now we need to calculate all the reactions at the fixed end. So we'll be having the horizontal force HD, vertical force that is VD, and moment. So sigma fx is equal to 0. If you apply sigma fx is equal to 0, that means horizontal forces along the beam. So we have only horizontal forces 34.64. That is HD. HD at the reaction point, that will be equivalent to HD is equal to 34.64 kilonewton. So no other horizontal forces. That's why it will be equal and opposite direction. So horizontal force it will be acting in this direction, means reaction will be in the opposite direction. Then sigma fy. Fy is equal to 0. So that means we need to calculate what is Vd. Vd is equal to, so what is the force acting here? 20 into 3. 20 into 3, that is the vertical force acting in the cantilever portion, and vertical force here 20 kilonewton. So 20 into 3 plus 20 is equal to 80 kilonewton acting at, so that is Vd is equal to, so you'll be getting 80 kilonewton, that reaction. Then you have to calculate the moment. Moment sigma md is equal to 0. What is md? That is the moment at fixed point. So that is equal to 20 into 3. So that is the total force acting at its centroid. So acting at its centroid means 3 meter will be there. It will be from B, it is 1.5 meter. Then from at D, 1 plus 1 plus 1.5. That's why here 3.5 meter will be there. So total distance from the D to the centroid of the load. So this half portion you have to take, and the remaining distance you have to add. That is why that is 3.5 will be there. Then 20 into 1. This is the perpendicular distance for this force, 20 into 1. Then we have the moment. Moment will be, that is acting in the negative direction, that is 14.25. So minus will be there. So total moment md is equal to 244.25 kilonewton meter. So this is the reaction we calculated. So we calculate horizontal force and vertical force and moment at the fixed point. So once if you know, so we need to calculate what is the shear force. Shear force calculation. So as you know that one at the section 1-1, there is no other load left side of that one. So that's why V11 is equal to 0. Then coming to V22, the shear force at the section 2-2. So we'll be having the force only UDL. UDL, that is 20 kilonewton per meter for a distance of 3 meter. So it will be acting downward. That's why it will be negative. From the section, if it is acting downward, it will be negative. 20 into 3 minus 60 kilonewton. So if you come to section 3.3, section 3.3, so there is no other load from section 2 to same value will be there. Shear force minus 60 kilonewton. Then coming to at section 4.4, so here you see we have one more load 20 kilonewton. So minus, all are acting left side downward. So minus 60 from the UDL, minus 20 for this concentrated load. So total shear force at 4.4, it will be minus 80 kilonewton. Then coming to at 5.5. So from here to here, so there is no load. Hence it will be same as shear force at 4.4. So shear force 5.5 will be equal to minus 80 kilonewton. Then at 6.6, so we should get 0. So what is the reaction we have here? So 80 kilonewton we have, minus 80 plus 80, that is 0. That means you should get 0 at that point. So you let us see how to draw the shear force diagram. So this is the forces acting here. Then, so we have the 0 here, and shear force at 2 is equal to 60 kilonewton. And from here to here, it will go horizontal. There is no other force acting. So 60 kilonewton. Then coming down 20 kilonewton. So that is 80 kilonewton. And it is coming horizontal again. From here to here, there is no load. So 80 kilonewton. And reaction will be having 80 kilonewton going up. So this is the shear force diagram for this cantilever. So what you notice here, at the free end, there is no shear force. So here shear force, it will be 80 kilonewton for the fixed end. Then let us calculate how to calculate the moment. So let us see the bending moment diagram. So MA, bending moment here at A, MB is equal to force into distance at the centroid distance of this UDL. So 20 into 3, that is a total force acting downward, and it's a hogging moment minus 20 into 3 into at its centroidal distance, that is 1.5. So that's why minus 90 kilonewton meter. So MB is equal to minus 90 kilonewton meter. Then MC, what are the forces acting here? So shear force, you have taken the same value, But moment you can't take like that. So moment what will happen, the total load into perpendicular distance it will go. So minus 20 into 3, here 1.5 for this centroid plus 1. So that's why it's equal to 2.5 will be there. So minus 150 kilonewton meter, the section before the couple. So you'll be having at this one. So if you see at the, if you consider the couple also, minus into 3 into 2.5 minus 14.25. That also you have to consider in the same direction. So total will be getting 164.25 kilometer meter. So section after the couple. So similarly, you have to calculate the moment at MD. MD is equal to, so again distance from perpendicular distance from here to here. So 20 into 3 negative direction because of hogging into the distance from 1 plus 1 plus 1.5, that is 3.5 will be there, minus the moment. Moment there is no perpendicular distance, that is the actual total moment will be there. So 14.25 will be there into the vertical force into the distance 20 into 1. So total moment will be getting minus 244.25 kilonewton meter at MD. Okay. So MD is equal to minus, if you take both, if you MD as well as this moment, it will be 0 at that point. That is a checking. So loading diagram, it will be as it is given here, and the bending moment diagram you see here. So moment will be 0 here. In the previous section we calculated at B we got 90 kilonewton meter. So it is hogging moment, and from here to here 150 kilonewton and 164.25 kilonewton and 244.25 kilonewton. This is the bending moment diagram for this cantilever. So you can see here the bending moment diagram. Bending moment at the free end it will be 0, whereas the fixed point will be more. So you should remember all these things. So simply supported it will be different, and for cantilever it will be different. So after knowing this one, let us go some of the examples problems given in the gate. So let us see, this is the frame. A frame ABCD is supported by a roller at A and is on hinge at C as shown in the figure. Then what is they're asking? The reaction at the roller end A is given by. Can you tell me what is the reaction? This is the options they are given. First option P, second option 2P, third one P by 2, and fourth one 0. Can anyone tell this one? So what will happen is we have only vertical forces here. So there is no horizontal force. If you take sigma Fy, so only the reaction will be coming for this hinge point. Since it's a roller, it cannot take the vertical force. It will, so only horizontal what will be there. So there is no horizontal force. Hence the answer will be D. So if we take all the sigma Fx, there is no horizontal force. Hence the reaction. So what you wanted, reaction at the roller end A is given by 0. In this case, it will be 0. So okay, clear? So since there is no horizontal force, if they give some horizontal force, then it will get sigma Fy is equal to 0. Whatever that force, it will be equivalent to that horizontal force. Since there is no horizontal force, so we will be getting 0 reaction at the roller end. So let us take another example. Consider the three prismatic beam with the clamped support at PQR as shown in the figure. So this is a figure you are seeing here, PQR. Given that the modulus of elasticity E is 2.5 into 10 to the power 5 MPa, that is MPa also equal to Newton per millimeter square, and the moment of inertia I is 8 into 10 to the power 8 millimeter to the power of 4. The correct comparison of magnitude of shear force S and the bending moment developed at the support is, so they are given the option here. You can see here PQR is the PU is a cantilever beam having the constant load at the end here. And Q, at support Q, you have the UDL 20 Newton per meter, and at the another one you will be having on the moment. So we have to calculate both the shear force and moment. You have to see which option is correct. So let us calculate what is the shear force. Shear force per P. So 80 into 8. So shear force will be 8, full 80 will be there here. So shear force here, so 20 into 8, 160. So shear force for the moment, there is no shear force, that is 0. So calculate the moment. Moment is equal to 80 into 8, that is 640 megapascal. And for this one, it will be having 640 megapascal. It will be curved like this. This is a parabola one, and this is a moment. It's a constant moment throughout. Now they ask us to tell which is the option is correct. So now you can see the shear force for P, Q, and R. So SP, so SP is less than SQ. So you see, this is the shear force at the fixed point, clamped point. So this will be SP is less than, okay, we compare one by one. So you'll be having option A, SP less than SQ, but not less than SR. That is not correct. So SP is not equal to SQ. That is not option, will not go. SP is less than SQ, okay, but is greater than SR. That is correct. Then you come to the options moment. All the moments you see here, MP, MQ, MR, all the moments at the support will be same. So this here also it will be there, but this option is not matching. So option C will be the correct answer. Okay. So now what you have done? We have calculated all the shear force for all the 3 beams with different loading condition, and also we calculate the moment and compare the shear force and bending moment. The beam having double cantilever attached at midspan is shown in the figure. The nature of force in the beam AB. Nature of force in the beam AB is. So they're asking 4 options will be there. Then also they're given AC. AC is equal to CB and CD is equal to CF. FG is equal to ED. So all these lengths are equal. So they're applying the load here. P is equal to here and P is equal to here. And what is the nature of force on the beam? What type of force is acting on the beam? They want to know. So they're telling options: bending and shear, bending, shear, and torsion, or pure torsion, torsion and shear. So if you both are vertically downward force acting at the different point at the same distance from C. Hence, it is only compressive force acting on the beam. So that means in the beam, it will be having both the bending and shear only. So it cannot have torsion. So if it is in the reverse direction, then it will be having the torsion. So here it will be having only compression force acting on the beam AB. Hence, it will be having both the bending and shear type only. So answer will be first one. So answer A. Okay. So we have to see that how the load is acting, whether it's acting both are downward or in the reverse direction. So reverse directions, it may be possible to have the torsion. And next problem, let us take the bending moment at the midspan X. So in the beam with the overhanging shown in the figure is equal to. So the bending moment in kilonewton, they are asking at the midspan location X in the beam with the overhang shown in the figure. So this is the figure they are given. So they want to know what is the bending moment at X. How to calculate here? So we have the hinged support here, and here we have the support here, spring support. So that can be written, the option they are given here, 4 options they given: 0, -10, -15, -10, -20. So this is the, this beam can be resolved like this. So we'll be having the overhang. So this spring you can write as it's having the reaction RB upward and RB downward for the spring. So once if you know this one, you can calculate the reactions RA, RB you can calculate. Once if you know the RA, RB, then you can calculate the moment X. Only thing they are confusing. What is this spring? Spring is nothing but having the transferring the force in vertical direction, in the same direction. So let us find out the reactions at A and B, and find the bending moment at X. Is very easy now. Once if you know how to resolve this one, then you can collect the reactions and bending moment. See, this is the value. RA is equal to 25 kilonewton will get, and sorry, RB is equal to 5 kilonewton. Then bending moment at X is equal to minus 15 kilonewton. So option will be C option, that is minus. They're already they're given here. Sometimes they give the units in the question itself. So they will not give here. So that's why it is C, minus 15 kilonewton meter. So okay, only the trick what they are given here, the spring element, in that direction it will be having that force. So spring is a vertical spring here. So we have the vertical force here. So similarly, if they give another spring at the horizontal direction, it will be horizontal force at that point. They should remember. So we'll go to next problem. So the portal frame shown in the figure is subjected to a uniformly distributed vertical load, that is W per unit length. The bending moment in the beam at the point Q is. So what are the options? Whether it's a 0 or a WL square by 24 or WL square by 12 hogging or WL square by 8 sacking. So here you see only we have the UDL on the beam QR. So there is no other load. So if it is a so you have the roller end here. Here hinge support is there. So what will happen? So if you have any horizontal force, then only it can resist. You will get some reactions at this point. Since there is no horizontal force, only vertical force, so it will be having only reactions. Here reaction, here reaction. There is no horizontal reaction. Once if it doesn't have any horizontal reaction, the moment at Q is so vertical force it will pass through here, and if you have the horizontal force, then horizontal force and the distance you have to measure. Since there is no horizontal force, so the answer will be 0 here. So they're confusing here. So that's why you should be remember clearly. So what is the reaction? What are the loads acting on the beam? So whether it's a UDL or any horizontal force is there, all the things you have to see. So suppose if they give horizontal force at Q some value P, then you will get the force at P also at equivalent to here. So there is no roller point, there is no horizontal force. At the P point only, we take the horizontal force H. So answer will be 0 for this one. Okay. So horizontal beam ABC is loaded as shown in the figure. The distance of the point of control fracture from the end A in meter is, this is the beam they given. So this is the fixed end, this is a roller end. They shown the loading here, kilonewton, 10 kilonewton. So they want us to calculate what is the point of control fracture from end A. What is the point of control fracture? Where the bending moment is 0. So you have to draw the bending moment for this beam. How to do that one? First, see, this is a cantilever portion that can be transferred like this. So we will be having the horizontal force, vertical force 10 kilonewton. So 10 kilonewton will be transferred here, and equivalent moment. That moment also will be there here. That will be coming. So 10 into the distance that will be coming here. So since the compatibility condition you have to take. So once if you know that this is as a cantilever, so you are converted fully into the cantilever with a reaction RB and force, then it will be transferred here, and also moment. So it will be, we'll be having the for cantilever 10 kilonewton vertical downward force, RB vertical upward force, and a moment. So compatibility, the what compatibility at the B, the deflection is equal to 0 at B. So what is the deflection for the cantilever beam? If you have a constant load at the end, that is WLQ by 3I EI. So this is the one for the vertical load, that is 10 kilonewton, 0.75 meter cube by 3 EI. Then we have the moment. Moment is equal to this is 1 meter. This is 10 into 0.25. So 0.75 will be there. So total 1 meter. So 10 into that is m L square by 2EI. That is the deflection for the moment. W, that is m L square by 2EI is the deflection at the, if we have the moment at the cantilever point. Then, so we have the minus sign, it will be acting upward, or RB into the distance, that is a 0.75 is the distance, that is the RB L cube divided by 3 EI. So 0.75 is the distance from here. So this is the equation. From this one, you can calculate RB is equal to 15 kilonewton. Once if you know the RB, then you can put this is the our beam now. So we have the RB we have, and the value of vertical force acting here, and the different distances, all the things are given. So now what you have to calculate? You have to calculate the point of lecture. You have to calculate the moment at a distance from here, at a distance x from the end if you take. So moment at x is equal to mx, that is 10 into x minus 15, that is the reaction 15 into x minus 0.25. This is the distance x minus 0.25. That is 1. So you will be getting x is equal to 0.7. From here to here, you will get 0.75. So point of contact lecture from the end A is equal to 0.25. So that is the point of contact lecture you are getting at a distance 0.25 from end A. So we have to write here 0.25 meter from. The next problem, let us take the bending moment diagram for the beam is given in the figure. The shear force at sections A and B you have to calculate. So this is the bending moment diagram. The distance, so they are having 100 kilonewton here bending moment and 200 kilonewton bending moment here. At a distance, this is 0.5 meter, 1 meter, 1 meter. So what this is the options they are given. So which one is correct? At AA and BB, we have to calculate the shear force. So this is for the portion, left side portion. This is the bending moment diagram. Since the bending moment is constant from here to here, there is no other force. That means we'll be having the moment at this point only. So here, AA will be, the shear force will be 0. So if you take for the portion section BB, so 200 minus 100, this is the inclination portion. So we will be knowing, so 200 minus 100 for the distance 2 meter. So that will be having inclined portion. The distance at the midpoint will be at 50. If you take the react moment mx at a distance 1 meter, 50 into 1. So our answer will be 0 at 1. AA it will be 0 and BB it will be 50 kilonewton. So you have to take the section here 200 minus 100. So you will be getting the ordinate here 50. So at a distance 1 meter, 50 into 1 meter. So you will be getting the shear force equal to 50 here. So here 0, here 50. So let us take another problem. So group 1 shows a different load acting on a beam and group 2 shows a different load bending moment distribution. Match the load with the corresponding bending moment. See, this is the different loading they are given. So they will be giving the option like this. So first one, group 1. So this is the P, it will be having only moment. Here a constant load, is a UDL, is a varying load. So one by one, if you check, so it is very easy. I think one stretch you can get sometimes if it is having option only one here. So if it is simply supported beam, we have a moment here. Throughout the moment will be constant. So fifth option here you see. So the moment will be constant throughout. So it is only option here B. So at one stretch you can put the answer B. But let us check for others also. So for Q, it is a constant load acting at the center point. So since it is acting at the center point, that it will be bending moment diagram will be having triangular portion. So if we have a UDL, it will be having parabola. So that means, so we will be matching almost for the 2, 4. For R, it will be 1. So R, it will be 1. And for the S, it will be 3. This is a cubic equation. So our option will be B is the correct answer. So what you guessed initially, without any calculation, also you done. Sometimes it will be possible. If you give 2 times, then you have to calculate for the both the times. Okay. So let us calculate one more thing. So match the list 1, that shear force diagram, that is the list 1 beams with the list 2 diagram of beams with the supports and the loading, and select the correct answer by using the codes given in the below. So this is the the given shear force diagram. So they are given ABCD. So they are given the loading system. So we have to match A to here different one. So that is again it is very easy. See here. So if you have a overhang portion like this, so we'll be having the loading at the overhang. Then the shear force will be only at the overhang portion. So that is B. B, it will be having this one. And for A, so it is having, so the options, let us see. Here the different options they are given. So let us see for the A. So the shear force, it will be 0 at this point, and you'll be having for the overhang portion here, that is L by 4, Q into L by 4, it's coming here. And we have the reaction. Since it's a reaction, it will going up, and again it will be inclined one. And see, this is a UDL, it's almost matching. A is equal to 3. A is equal to 3, and B is equal to for the 1. Portion is a constant load, so it will be matching with the 2. So for example, if you have the shear force here, the shear force will be downward here, and it will be constant for this distance, and it will be coming upward, and up to the reaction it will be going up here, and it will be constant here, and again at the center point you have a constant load, it will be coming down, and again it will be constant, and for the reaction to go up, and it will go horizontally and again down. So this is Q by 2. So then the D, it will be, so it will be having only forces like this in the fourth one. So options you see, this is the first one. So A is equal to 3, what you have guessed is correct. This is fully UDL portion. So this is the inclined portion is there. And B, it will be first one. So B is equal to 1 will be there. So overhang portion only loaded with UDL. And C, it will be having the second one. So the four forces acting like this in the second one. And D, it will be having only overhang loads. Okay. So then let us take one more problem. So it will, for the simply supported beam of length subjected to a uniformly distributed moment. So we have the uniform distributed load m kilonewton per meter per unit length as shown in the figure. Then the bending moment in kilonewton meter at the midspan of the beam. So throughout the beam, it will be having like a UDL. You will be getting the moment kilonewton meter per unit length. So they ask us to calculate what is the bending moment at the center point. So what will happen? This is the option they given: 0, m, ml, and m by l. So let us calculate the reaction at the right support. That is VR. It will be upward. So taking the moment about the left hand support, we get VR into L minus M into L. M is equal to per unit length. For a length L, M into L. So that will be 0. So that's why reaction VR is equal to, we are getting M. So then the reaction at the left hand support VL will be the M downward. So since it is upward, the reaction will be downward. So take the moment at the midspan. So we will be having at the midspan. So it will be acting downward moment M downward at a distance L by 2. So M into L by 2. And we have the moment, all the moment at per distance L by 2. So M into L by 2. that will be positive. This will be negative. Okay. So that will be, you will be getting 0. So that means, so whatever the distance you measure from the end, so you'll be getting the bending moment 0. So that means bending moment throughout the beam is 0. So option will be A. First option is correct. So we will go for now simple stress strain and their relations. So first of all, we should know what are the types of load. So if we take a beam, the loads are defined as a set of external force acting on a mechanism or engineering structure. Common loads in engineering application are either tension or compression. Tension means is a direct pull. For example, force present in the lifting hoist. So it will be having a full tension. That is a direct pull. So compression, that's a direct push. For example, force acting on the pillar. If you have in a building, all the forces coming from upside, it will be compression. So sign convention for the tensile force positive, compressive force it will be negative. So these are the different types of load. And what are the loading types? So you might have seen that a dead load, it's a static load. It will not change. It is a non-fluctuating force generally caused by gravity. Live load due to dynamic effect. That means it will be moving from place to place. It will not be constant. Load exerted by the lorry or on a bridge. It will be moving on the bridge. Impact load or the shock load. Due to sudden blows, sudden impact will be there on any object. It will be impact load. Fatigue load, it is a fluctuating or alternating load. So magnitude and the sign of a forces will be changing with the time. So for example, if you go to any seashore, you'll be having the waves will be coming and going. So both will be having tension and compression. If you have a structure built on the shore, both it will be having tension and compression. So it will be fluctuating, alternating loads. So let us see what is the material subjected to the external force. A resisting force is set up within the component. This internal resistance force per unit area is called the stress. That means stress is equal to per unit area. Force divided by area is called the stress. So what is the SI unit for the stress? So it will be Newton per meter square. So it can be either kilopascal or megapascal or gigapascal or terapascal. It will be like this. And megapascal, it's also equal to 1 Newton per millimeter square. That's equal to 10 to the power of 6 Newton per meter square. So usually, most of the times you'll use MPa, that is a megapascal. Megapascal, that is 1 Newton per millimeter square. So also equivalent to 10 to the power of 6 Newton per meter square. So what is the strain? When a body is subjected to some external force, there is some change of dimension of the body. So the ratio of a change of dimension of the body to its original dimension is known as the strain. So whatever the change will be there, small change in length divided by the original length. It's called the strain. Strain is that is length divided by length. It is a dimensionless quantity. So it can be represented like this. There will be maybe tensile strain, compressive strain, volumetric strain, or shear strain. What is a tensile strain? Is a ratio of increase in length to the original length of the body when is subjected to a pull force. Compressive force is a ratio of decrease in length to the original length of a body when it's subjected to push force. Volumetric strain, the ratio of a change in volume of the body to the original volume. So it is called a volumetric strain. And shear strain. So you'll be having the shear type. It will be having on a surface that shear due to shear stress. I will explain next that one. So you will be having different type of stresses. Stress can be divided into direct stress, indirect stress, and combined stress. Direct stress again divided into shear stress and normal stress. This normal stress is the tensile stress and compressive stress. Then the indirect stress you'll be having. So it will be having torsional stress as a bending stress. So you can see this all the directly push or pull, whereas the indirect stresses will be the due to bending, due to tension or compression or bending. And type of stress. So uniaxial state of stress. So if you have a only uniaxial force, this uniaxial force, it will be having the area and you will be pulling or pushing, it will be there. And the biaxial state of stress. So both the x and y. So it will be active. So sigma, that is sigma xx and sigma yy, both the stresses will be acting in different phases. And the triaxial state of force, all the three phases will be loaded. So in the uniaxial, it will be one phase will be loaded. In the biaxial, two phases, both the phases will be there. And the triaxial, for all the phases will be there. Here, biaxial, top and bottom, left and right. In the uniaxial, left side and right side. Whereas in the triaxial, for all the phases will be in different stresses will be there. Then the tensile and compressive stresses. Tensile stresses, it will be pulling type, and compressive type is the pushing type. So these are the different types of stresses. Then, so also the bearing stress. So when an object is supports on a soil, it will be having the bearing stress, bearing type of stress, that is a contact on the surface. And you will be having the shear stress. So if you will be having the shear, it is tangential to the surface. Force acting parallel to the area concerned. That is the tangential, that is the shear force. So bending stress is a combination of tensile, compressive, and shear stresses. Torsion stress encountered in twisting of a shaft. So if you twist a shaft, it will be having shear stress, or twisting moment will be there, is a shearing stress. So what are the tensile stress? Is a tensile resisting force divided by cross-sectional area. That is the force divided by area. That is the tensile stress. And compressive resisting force divided by cross-sectional area is the compressive stress. And shear stress will be the total tangential force divided by area over which it acts. Strain is equal to, that is epsilon is equal to change in length divided by original length, delta L by L. So change in length, it may be extension or shortening. So extension will be like this. If you pull both the sides, it will be having the extension. And you will be have the forces. The resisting force will be, it will be there here. Resisting force P, it will be equivalent to P, it will be there. And similarly, resisting force will be here. And if you take the element, it will be acting at the stresses will be at the element will be like this. And similarly, if you see here for the compressive force, so it will be like this, that the resistive force will be there. And similarly, if you see the shear strain phi is equal to tan phi, that's equal to delta L divided by H. What is the H? So that is equal to delta L by H. That is shear strain. Then you will see what is the elasticity and the elastic limit. The property of material by virtue of which it returns to the original shape and size upon removal of a load is known as elasticity. So similarly, if you see the stress correspond to the limiting value of the external force up to and within which the deformation disappears completely upon the removal of external force is called the elastic limit. So we know the elasticity and elastic limit. So we will see what is Hooke's law. Hooke's law, it states within elastic limit. That means it will be, if you remove the force, it retains. That is within the elastic limit, the stress is proportional to strain. That means it will be straight line. So if you see the E is equal to stress by strain, where E is the Young's modulus, or it also called modulus of elasticity or elastic modulus. Hooke's law holds good equally for tension as well as compression. So what is the Poisson's ratio? So Poisson's ratio is the ratio of lateral strain to the longitudinal strain produced by a single. The symbol of Poisson's ratio will be mu, or in some books they will be using 1 by m. So what is the factor of safety? Factor of safety is the ultimate stress divided by permissible stress. These are the basic things you should remember: the Hooke's law, Poisson's ratio, and factor of safety, both elasticity and elastic limit. Then we'll see that one, what are the deformation of a body due to load acting on it. So we know the elastic Young's modulus, stress by strain, that is sigma divided by epsilon, and strain is equal to stress by E, Young's modulus. So you can calculate the epsilon strain, stress divided by E. So we know what is the stress is equal to P by A. So P by A into E. So you can write strain is equal to delta L by L. That is change in length divided by origin length. So deformation delta L is equal to PL by AE. So any thing if you take that change in length is equal to PL by AE, you will be getting. So modulus of rigidity. For elastic material, it is found that a shear stress is proportional to shear strain within the elastic limit. So now always you are talking within the elastic limit. The ratio is called modulus of rigidity. It is denoted by the symbol G or in some books C. So G is equal to shear stress by shear strain. That is shear stress tau divided by phi. It will be there, Newton per millimeter square. All the stresses will be always Newton per millimeter square. And the bulk modulus is called K. It is defined as the ratio of volumetric stress to the volumetric strain. It is denoted by the symbol K. And K is equal to volumetric stress divided by volumetric strain. That is sigma divided by epsilon V. That is Newton per millimeter square. So let us see what is the relation between this elastic constant. This is very important. I think we should know all the things about the relation between the modulus of elasticity and bulk modulus, and we can derive that one. And I will not go into the derivation here. I will give the values. E is equal to 3K into 1 minus 2 mu. So the relation between E and K and also mu will be there. So relation between the modulus of elasticity E and modulus of rigidity G, will be getting E is equal to 2G into 1 plus mu. And similarly, the relation between among all the three constants, constant E, G, and K will be E is equal to 9kg divided by G plus 3K. So we should remember all these constants, and sometimes they will ask in the GATE exam. So we'll see that one. So stress strain diagram of a uniformly loading ductile or brittle material. So stress strain diagram of a mild steel, if you see, so mild steel, how you will do the tensile stress under the UTM, that is ultimate testing machine. So the specimen may be circular cross section, or it may be rectangular cross section. So we will be getting the stress strain diagram like this. So if we have the plot of stress versus strain, so we'll be getting the so this is the elastic limit. So you can see here point A is called limit of proportionality or the proportionality limit, and point is B is the elastic limit. So that means whatever you're linking is the elastic limit, it will be holds good for all our Hooke's law and all within this limit only. So point C and D, that is upper and lower yield points, and you will be having the yield stress will be there here. So that is then you will be go to point E. That is point E is the ultimate or tensile strength of the material. So we will get the ultimate stress here. And further, if we go, it tries to break that one. That the fracture will happen, and we will be having the breaking of the element. That is a fracture point at point B, and the cone formation will happen at this point, the rupture point. So what will happen in the case of ductility material? The capacity of material is to allow the large deformation. That means you will be having a large deformation at this level, or the large extension without failure is called the ductility. And brittle material is one which exhibits a relatively small extension or deformation of fracture. That means it will be sudden. It may break at this point only. So it will not further. It will not go. So that's why it is called a brittle material. Then constitutive relationship between this stress and strain. So we have one-dimensional case, that is E is equal to stress by strain, and if we have a two-dimensional, we'll be having both the x direction and y direction. The longitudinal strain is always opposite to that of the lateral lateral strain. That is, the longitudinal strain is the tension means lateral strain will become compressive and vice versa. Every longitudinal strain is accomplished by lateral strain in orthogonal direction. So ratio of, already we know that ratio of lateral strain to longitudinal strain is called the Poisson's ratio mu. So mu is equal to minus lateral strain divided by longitudinal strain. So that will be, we can give mu is equal to delta L is equal to change in length. Delta B is here in the two-dimensional B direction. The decrease in breadth. So will be decreasing, will be extension will be there, and decrease in the breadth will be there. Delta D is equal to decrease in depth. The longitudinal strain is equal to delta L by L. So lateral strain is equal to delta B by B or delta D by D. So the strain along x direction due to sigma x. So we will be having the sigma x in the x direction, that is sigma x by E. Strain along x direction due to sigma y, that is equal to minus mu into sigma y by E. So if we take the combined effect, that is total strain either in x direction or y direction, epsilon x is equal to sigma x by E minus mu into sigma y by E. Similarly, the total strain in the vertical direction, that is y direction, epsilon y is equal to sigma y by E minus mu into sigma x by E. If you take the three-dimensional one, so you'll be having the x direction sigma x equal to sigma x by E. Strain along x due to sigma y is equal to minus mu into sigma y by E. Strain along x due to sigma z is equal to minus mu into sigma z by E. So if we calculate that the total strain in the x direction, so we will be getting the epsilon x is equal to sigma x by E minus mu into sigma y by E minus mu into sigma z by E. So you can see x, y, z. So first one will be positive, both other two will be negative. So epsilon y is equal to y. So x is equal to x, y is equal to y. Then x, y, z, it will be in the cyclic order. So y, z, x. So sigma, epsilon z is equal to z, x, y. So other two will be negative direction. So let us see that consider analysis of bar varying cross section. So consider a bar of a different length, of different diameter, and having the cross section like this, as shown in the figure. Then the bar subjected to the axial force P. So we'll be having the sections for different cross section A1, A2, A3, and we will be know the total change in length is obtained by adding the changes in the length of the individual sections. So we'll be having the whatever the length L1, L2, L3, the change in length you have to calculate for individually, that delta L is equal to, so for the portion first one, that is P L1 by AE1, A1 E1 plus P L2 divided by A2 E2 plus for the third one P L3 by A3 E3 P, if you take component, it will be there here. For the same E value, the equation reduces to P by E into L1 by A1 plus L2 by A2 plus L3 by A3. So this is a simpler, if you have the different lengths and different diameter or cross-sectional area. So you can do like this. For change in total change in length is equal to P by E into L1 by A1 plus L2 by A2 plus L3 by A3. So similarly, if you calculate analysis of uniformly tapering circular rod. So consider the bar uniform tapering. So that means it will be having a diameter D2 at the top and diameter D1 at the bottom. So you'll be having like this, and P is the load acting at the vertically here and downward here, and total length is the total length L, and Young's modulus of the material E, and the total elongation. That means we have the circular cross section, that is tapering from top to bottom to 4PL divided by pi E D1 D2. So remember here, it will be circular section at top and bottom. So what happens if you have a rectangular bar? So consider uniform tapering from one end to other end. That is a section. It is a rectangular, not diameter. It's a rectangular section. A by A crossing at the bigger end and B by B at the smaller end, like this. So we have the cross section like this. It's not diameter. Okay. So A by A, B by B will be there. Then what is our total elongation? Total elongation will be PL by E into AB. So this is thing you have to remember. If you have the section, if you give in our problem, you have to remember all this formula. If you have a rectangular bar or rectangular tapering bar or a diameter, that is a tapering diameter, circular bar, and sometimes they'll give with a constant thickness. So it will be having a uniform tapering rectangular in the front side. If you see, if it's a tapering rectangular one, if you see in the perpendicular direction, it's only constant thickness. In that case, so what will happen? That it will be like this. So you'll be having the smaller breadth here, B, and A is equal to bigger one. It will be having the thickness T in the perpendicular direction. Then what will happen? That P is the load acting on that one, L is the length of the bar, E is the Young's modulus, T is the thickness of the bar, and total elongation due to this bar PL by ET into A minus B into logarithm of natural logarithm of A by B. So this is the total elongation if we have a constant thickness element. So now elongation produced in a bar due to its self weight. Sometimes you should know that also. So consider a bar of uniform diameter. So density, so it will be having the uniform diameter. So density of the bar is equal to rho. A is the cross section area of the bar, and P is the self weight of acting on the bar, that is rho G A by into L. L is the length of the bar. E is the Young's modulus of the bar. Then the total elongation due to self weight is equal to PL by 2AE, half of that one. So you know that one, if you have an external load, that will be elongation will be PL by AE only. So due to self weight, it will be PL by 2AE. So the thermal stress is another one that we should know how this thermal stress will be acting. Consider a body which is heated to a certain temperature. So L is the original length of the body, delta T is the rise in temperature, E is the Young's modulus, alpha is the coefficient of linear expansion, delta L or dL is equal to extension of the rod due to rise in temperature, and we will be having the rod. If the rod is free to expand, then the thermal strain developed will be epsilon T is equal to delta L by L is equal to alpha, that is alpha into delta T, that is the coefficient of linear expansion for the change in temperature, delta T. So the extension of the bar delta L, you can calculate L into alpha into delta T. If the body is restricted from expanding freely, the thermal stress, I think thermal stress, most of the times they will ask what is the thermal stress developed in the body due to rise in temperature. That is sigma T divided by epsilon T is equal to E. See here, there is no variation of length. So stress will be independent of length. So sometimes they will confuse in the problem. So sigma T is equal to E into alpha into delta T. So that you should remember all the things. I think here only delta L is equal to will be having the extension of the rod will be having the, in terms of L and alpha, whereas in the thermal stress, so it will be independent of length. The stress and strain due to support yield. If the support yield by an amount equal to delta, then the actual expansion is given by the difference between the thermal strain and the delta. So whatever thermal strain you are getting here, epsilon is equal to L into alpha into delta T minus delta. That is our yield, support yield by an amount delta divided by L. So that is the one epsilon. Then actual stress is equal to, similarly here you can see here, actual stress is equal to strain divided by E into E, sorry. So compound bar, sometimes they will be having the compound bar like this. So you'll be having the different bar, different materials and different lengths and cross-sectional area and Young's modulus, everything different. Then they ask us to calculate the change in length, common extension. So if we have like this, the common E will be the product of X modulus into area for all the elements divided by A1 plus A2 plus A3, etc. The numerator sum of the product X modulus into area. So for all the elements will be there. So common E is equal to sigma of EA divided by sigma of A. So you may be knowing in the calculation of centroid, similar you are doing here. So the stress in the equivalent bar. So whatever equivalent bar will be there, stress is equal to W divided by total area. So sigma A will be there. Strain in the equivalent bar is equal to W divided by that equivalent Young's modulus into sigma of A, that is X by L. So E is equal to stress by strain. So a common extension, that whatever extension we wanted to calculate, X is equal to WL by E into A. So that will be there here. So extension of a single bar. So it will be acting as it's a rigid bar connected here. So all the element will be going common extension. So that's why you'll be having that common extension X is equal to WL by, that is how external force W, total length will be L will be there, and divided by F, E C into sigma A. So let us take some examples in this simple stress and strain. Consider a stepped bar made up of linear element elastic material subjected to an axial load 1 ton as shown in the figure. So segment 1 having the cross section of 100, cross section A1 is equal to 100 millimeter square, cross section 2 is 60 millimeter square. Young's modulus for the first one is equal to 2 into 10 to the power 8 megapascal. For the second element, it will be 3 into 10 to the power 5 megapascal, and having the lengths L1 is equal to 400 millimeter and L2 is equal to 900 millimeter. Then they ask us to calculate what is the strain energy in the bar due to the axial load. You have to calculate the strain energy. So that means you have to calculate what is the elongation. So elongation will be the total elongation due to L1 plus L2. So both the element you have to calculate. So element 1, so they are given the different options. Element 1, so element 1 is L1 you calculate, that is the delta 1 is equal to PL1 by E1 A1. Sorry, E1 also you have to put here, E1 A1. So calculate the delta 1. Similarly for the element 2, calculate delta 2. Then sigma total elongation is equal to 0.07 millimeter. So once if you know the elongation, that the total strain energy is equal to half into P into delta. So you'll be getting 35 Newton millimeter. So option will be C, option is correct. So next you take the bar having the diameter, varying diameter from 20 mm to 10 mm is connected to another uniform rod of diameter 10 mm as shown in the following figure. Both the bar of the same material. Here they are giving the E value same for both material, and when subjected to load P, that is P is equal to 30 pi, the deflection at the point A is what they have to calculate. So, so we have the tapering element here. So deflection for that one will be delta 1 is equal to 4P L1 divided by pi E D1 D2. So we know all the D1 D2 everything you know. Substitute that one, you will be getting the delta 1 for this portion, and similarly calculate for the second element. So second element will be a full circular one, same diameter. Sorry, this will be 10. 10 it will be there here. D2 is equal to 10. So element, so you calculate delta 2, 4P L2 pi E D2 square. So here 10. So calculate delta 2. So delta 1 and delta 2 will be the total value. That is 15 millimeter. So another example, you take an isometric body is in a hydrostatic state of stress as shown in the figure. For no change in the volume to occur, what should be the Poisson's ratio? So now they're giving the different options. Now we have to calculate there is no change in the volume. So what is the Poisson's ratio? That means we know the volumetric strain epsilon v is equal to sigma x plus sigma y plus sigma z divided by 3 into 1 minus 2 mu. So they're telling delta v by v. So this is the volumetric strain. So that means the delta v is equal to 0. That means we will be equating first portion and second portion. That is either this portion will be 0 or the second portion will be 0. So this cannot be 0. So second portion is equal to 1 minus 2 mu is equal to 0. So mu is equal to 0.5. So that what they are giving volumetric strain. So that will be volumetric, calculate the volumetric strain. From that one, you calculate the total. That is a change in the, there is no change in the volume. So that is delta V is equal to 0. That condition we have put. So we got the mu is equal to 0.5. So another problem, let us take another problem. So it will be having a elastic bar of length L with uniform cross-section area A, coefficient of thermal expansion alpha, Young's modulus E is fixed at two ends. The temperature of the bar is increased by T, resulting to a axial stress sigma. Keeping all the other parameters unchanged, if the length of the bar is doubled, then the axial stress would be, so now they are confusing. If the length of the bar is stress, they ask us to calculate what is the thermal stress. The thermal strain developed is equal to, this is epsilon T is equal to alpha into delta T, and you will be, if the body restricted from expanding freely, the thermal stress will be developed is equal to sigma T is equal to E into alpha T into delta T. So length has no effect on that one. So hence that the stress, actual stress is only sigma. So option A is correct. Take one more example. So the number of independent, the relation, independent constant for a linear elastic isotropic and homogeneous material. So if you have a elastic isotropic and homogeneous, so that will be a number of independent elastic constant will be 2. So that is 1. If you have a orthotropic 9 and as anti-isotropic it will be 21. So answer will be C. So another example let us take, and a metal bar of length 100 mm is inserted between two rigid balls and its temperature is raised by 10 degree. If the coefficient of thermal expansion is 12 into 10 to the power minus 6 per degree centigrade, and the Young's modulus is 2 into 10 to the power 6 megapascal, the stress in the bar is, so it's very simple here, alpha into delta T into E. So it is 24 megapascal. Okay, so this is a very simple, and answer will be C. So let us take one more. I think this you know that already. You know the relation when the for an isotropic element, the relation between the Young's modulus and the shear modulus and the Poisson's ratio mu is given by. So we know that E is equal to 2G into 1 plus mu. So what is that? Here you can get option will be G is equal to E divided by, first option is correct. So sometimes they'll ask like that also, so that you should know all the relation between the elastic constants. So rigid bar is suspended by 3 rods made of the same material. The area and length of the rod are 3A and L respectively, while the other 2 bars will be having like this. So we will be having the length is equal to here 2L, here L, area 2A, here 3A. So both will be connected like this. Outer bars, if the outer rods will be having the 2A and 2L, inner rod will be having 3A and L. If the downward force of 50 kilonewton is applied to the rigid bar, the force in the central and each of the outer bars will be. So now you know the condition. So 2 times of P0 plus PC is equal to 50. That is the your equilibrium condition. So then you will be have the compatibility condition that what is the deflection, the common deflection will be there. So you can equate to that one, P0 L0 A0 into E. So equate to that one, you will be getting the second equation. So by solving equation 1 and 2, so we'll be getting the value PC is equal to 30 kilonewton and PO outer element equal to 10 kilonewton. So for today, I will stop here. In the next class, I will continue for other portions. That is two-dimensional forces and principal stresses. And also I will take beams, beam deflections in beams and columns. I will cover in the next lecture. So for today, it will be done for the bending moment and shear force diagram and simple stresses and strain and their relations. Thank you. Good luck.
Thank you, Professor, for your informative session. So we have come to the end of the session now. So I thank all the participants for your enthusiastic participation. So I request everyone to please log in tomorrow between 11 to 12:30 for engineering mathematics session by Professor Shweta, Department of Mathematics, VVC Mysuru. Participants, please kindly fill your feedback form in the YouTube chat box already. So see you all tomorrow. Thank you, everyone.